Two spacecraft were launched in 1977. They were designed for a 5-year mission. Nearly 50 years later, they are still transmitting, not from nearby, not from the neighborhood of Jupiter or the rings of Saturn, where their instruments were originally aimed. From billions of miles beyond all of that, from a region of space no human-made object had ever reached before, their transmitters produce roughly 20 watts of power, less than a dim hallway light. Their computers hold about 69 kilobytes of memory, and yet every day, engineers point one of the largest antenna systems ever built towards a precise location in the sky and wait for a signal that takes more than 20 hours to arrive. The signal still comes. That persistence alone would be worth telling. But the deeper story is what these two spacecraft found after the 5-year mission ended and the decades kept passing. Because their most unexpected discoveries did not come from Jupiter. They did not come from Saturn. They came from the edge, from the boundary, where the sun's reach finally gives way to something thinner, darker, and far less familiar than anything a spacecraft had ever measured. They came from a place that scientists thought they understood. And Voyager proved that understanding was only the beginning. 7 discoveries. 7 ways the edge of the solar system turned out to be stranger, farther, and more complex than the models had prepared anyone to expect. First, the boundary itself was farther away than many earlier estimates had placed it, not by a small margin, but by billions of miles. Then, the shape of the region surrounding our sun was more complex than the cleanest simulations had suggested. Then, that boundary was not fixed. It moved, expanding and contracting in response to the sun's own activity, breathing in ways many models had not captured. Then, a hidden structure appeared inside the boundary, a channel of accelerated particles that few models had anticipated in that form, which scientists would eventually call the magnetic highway. Then, the space beyond the boundary was not the clean, empty medium that textbooks described. Then, the magnetic field at the crossing point did not behave the way many models suggested it should. And finally, solar storms, violent eruptions from our own sun, were still leaving detectable echoes in interstellar space, long after crossing a boundary where the sun's direct influence was expected to fade into the galaxy around it. 7 findings, each one a quiet revision to a confident model. Each one arrived at slowly, over years, by 2 machines that were supposed to have gone silent long before they got anywhere near that edge. We will come to each discovery in time, but to understand what Voyager found, it helps to understand how it came to be there at all. The year was 1977. NASA was operating under tighter budgets than the Apollo era had required. The space race had cooled. A mission to study Jupiter and Saturn was approved, practical in scope, ambitious in execution, and limited in duration. 5 years. 8 scientific instruments on each spacecraft. Photograph the gas giants, measure their magnetic fields, study their moons, then let the power fade. That was the plan. But a small group of mission planners had identified something in the orbital mechanics that was too rare to ignore. Every 176 years, the outer planets of the solar system, Jupiter, Saturn, Uranus, and Neptune, arrange themselves on one side of the sun in a rough alignment that makes sequential visits possible using gravity alone. A spacecraft swinging past Jupiter picks up speed from the planet's gravitational field without burning additional fuel. That added velocity carries it to Saturn. Saturn does the same for Uranus, Uranus for Neptune. All four outer giants visited in a single continuous journey, with each planet effectively paying for the trip to the next. This alignment occurs once every 176 years. It was open in the late 1970s, and it would not open again until the 22nd century. The launch window was narrow, a matter of years, and it was open right then. NASA moved. Voyager 2 lifted off from Cape Canaveral on August 20th, 1977. Voyager 1 followed 16 days later on September 5th. Despite launching second, Voyager 1 was aimed along a faster, shorter trajectory designed to bring it to Jupiter ahead of its counterpart. The names reflect arrival order, not launch order. Voyager 1 would reach the outer planets first, and so Voyager 1 it became. Voyager 1's path was shaped by one particular priority: a close flyby of Titan, Saturn's largest moon, which was known to have an atmosphere, and was considered one of the most scientifically valuable targets in the outer solar system. That flyby bent Voyager 1's trajectory sharply, carrying it up and out of the plane of the solar system, ending any possibility of continuing to Uranus or Neptune. It would travel alone, outward, in a direction no further planets would interrupt. Voyager 2 took a gentler arc. It reached Jupiter in 1979, Saturn in 1981, and then, in perhaps the most quietly extraordinary sequence of the entire mission, continued on to Uranus in 1986 and Neptune in 1989. No spacecraft before or since has visited all four of the outer giants. Voyager 2 remains the only one, but even as the planetary encounters ended, the spacecraft kept traveling. Their power systems, radioisotope thermoelectric generators, which convert the slow decay of plutonium-238 into electricity, continued producing usable current, not much current, and slightly less with each passing year as the plutonium decayed. But enough to power the remaining instruments, enough to keep the transmitters broadcasting, enough year after year to keep sending something home. The 5-year mission refused to end. There is a particular quality to the technology these spacecraft carry, and it is worth pausing on. The onboard computers were built in the early 1970s, using the best components available at the time. Each has roughly 69 kilobytes of usable memory. A single second of compressed audio on a modern device occupies more space than that. The tape recorders used to store scientific data before transmitting it to Earth are physical, magnetic, mechanical, the same fundamental technology that recorded music onto cassette tapes. The gyroscopes that help the spacecraft orient themselves have been running continuously for nearly half a century. The attitude control thrusters, tiny jets used to point the antenna toward Earth, have fired hundreds of thousands of times and are still responding to commands. The transmitters operate at about 20 watts. For comparison, a typical cell tower broadcasts at tens of thousands of watts. Voyager's signal, after traveling 15 billion miles through the vacuum of space, arrives at Earth so faint that it must be painstakingly separated from the natural radio noise of the cosmos using dishes up to 70 meters across, some of the largest antennas ever constructed. Even then, the engineers must filter carefully before anything useful can be read, and yet the signal arrives. It carries temperature readings, magnetic field measurements, particle counts. It carries information about a region of space that no instrument had ever sampled before these two machines passed through it. The people who built Voyager built it to survive 5 years in space. They did not build it to last 50. What they did was build it carefully, with redundant systems, conservative engineering margins, and components tested well beyond their expected operational range. The spacecraft survived because the people who made them left almost nothing to chance within what they could control. What they could not control was the universe itself. And the universe, it turned out, was gentler in some of the ways that mattered most. There were no catastrophic collisions in the asteroid belt, no unexpected radiation surges at Jupiter strong enough to permanently disable the instruments, no single-point failures that cascaded into silence. The spacecraft passed through decades of deep space and kept working. That endurance is not incidental to what Voyager discovered. It is the reason the discoveries were made at all. The boundary of the solar system was far enough away that only a spacecraft built with that kind of durability could reach it. And what waited there was unusual enough that having instruments capable of measuring it, even aging, low-power instruments from 1977, changed what we know about the solar system we live in. Scientists, in the decades before Voyager arrived at the edge, had thought carefully about what that edge would look like. They knew the sun continuously releases charged particles, the solar wind, flowing outward in all directions at several hundred miles per second. They knew this wind could not expand forever. Eventually, it had to encounter the thin gas that fills the space between the stars, the interstellar medium, and where the two met, a boundary would form. They had built mathematical models of that boundary. They had run simulations. They had produced predictions about where it would be, what shape it would take, and how a spacecraft passing through it would register the change. The models were built on real physics. The predictions were honest estimates. The broad structure they described, a slowing of the solar wind, a compressed boundary region, a definitive crossing into interstellar space, turned out to be correct in its general outline, but the details were wrong. Not recklessly wrong, not embarrassingly wrong. Wrong in the way that careful science often is when it reaches beyond what instruments have directly measured and into territory that can only be confirmed by going there. The boundary was farther away than the models predicted. That was the first surprise, and it is where the story of what Voyager actually found begins. The edge of the solar system is not a wall. There is no surface to cross, no visible line drawn across space where one thing ends and another begins. What exists instead is a balance, a continuous, dynamic negotiation between the outward pressure of particles streaming away from the sun and the inward pressure of the thin gas and magnetic fields that fill the space between the stars. That balance shifts, it breathes. It responds to the sun's changing output and to the subtle variations in the interstellar environment through which our entire solar system moves. Understanding where the solar system ends means understanding that balance. And to understand the balance, it helps to begin at the source. The sun does not simply sit still at the center of the solar system, radiating light and warmth into a quiet surrounding space. It is constantly moving matter outward. Every second of every day, the sun releases a continuous stream of charged particles, protons, electrons, and heavier ions, accelerated to tremendous speeds by the intense heat of the solar corona, the outermost layer of the solar atmosphere. This stream is called the solar wind. It does not blow gently. Near Earth, the solar wind travels at somewhere between 300 and 800 kilometers per second, depending on solar activity. That is roughly 1 million miles per hour. It is not a wind in any atmospheric sense. It is a plasma, a state of matter so energized that electrons have been stripped away from their atoms entirely, leaving a fast-moving, invisible river of charged particles pouring outward in all directions, filling the space around the sun in a continuous flood. The solar wind was first predicted theoretical in 1958 by physicist Eugene Parker, who calculated that the sun's corona was so hot, millions of degrees, that the outermost gas simply could not be held in place by gravity. It had to be flowing outward constantly. The prediction was controversial when it was made. Some scientists doubted that such a continuous outflow could exist, but within a few years, early spacecraft confirmed it directly. The solar wind was real. It was continuous. It touched every planet in the solar system and filled the space between them. As the solar wind flows outward, it carries with it the sun's own magnetic field, stretched and wound into a vast spiral structure by the sun's rotation. This magnetic field fills the solar system the way a scent fills a room, present everywhere, weakening with distance, but never entirely absent until something else takes over, and something else does take over. Eventually, the space between the stars is not truly empty. This is one of the less intuitive facts about the galaxy, and it is central to understanding what happens at the edge of the solar system. Between the stars, spread across the enormous distances separating one stellar system. From the next there is gas, extremely thin gas, mostly hydrogen and helium, with traces of heavier elements. In the part of the galaxy where our solar system resides, the density of this interstellar medium is often less than 1 particle per cubic centimeter. To put that in perspective, the air you are breathing right now contains approximately 10 billion atoms per cubic centimeter. The interstellar medium is, by any practical standard, an almost perfect vacuum, but it is not nothing. That thin gas has pressure. It has temperature. In our local neighborhood, a few thousand to tens of thousands of degrees. Though at such low densities, temperature means something different than it does in everyday experience. The interstellar medium also carries its own magnetic field. The galactic magnetic field, organized on scales far larger than any single star system, and it carries cosmic rays. High-energy particles, mostly protons, accelerated to enormous speeds by supernova explosions and other violent events elsewhere in the galaxy, streaming through interstellar space in all directions continuously. The interstellar medium is not still. It has its own momentum, its own structure, its own character, and our solar system is moving through it. The Sun and all its planets traveling around the galactic center at roughly 220 kilometers per second, meaning the interstellar medium, from the Sun's perspective, is a headwind blowing in from one direction, while the solar wind pushes back against it from all directions outward. Two flows, two pressures, pressing against each other across an enormous distance. Where they meet, something forms. Scientists call the region dominated by the sun's outflowing particles the heliosphere. It is, in the most literal sense, the sun's sphere of influence, the volume of space in which the solar wind defines the environment. Picture an enormous protective bubble, invisible to the eye, surrounding the sun and every planet in its family. Within this bubble, the solar wind fills the space between planets like an invisible river, flowing simultaneously in all directions outward. The sun's magnetic field threads through it. The environment for billions of miles in every direction is shaped by our star. The heliosphere acts as a kind of shield. The interstellar medium carries galactic cosmic rays, those high-energy particles accelerated by distant stellar explosions, and without the heliosphere, those particles would flood the inner solar system freely. Instead, the outward pressure of the solar wind deflects many of them, reducing the cosmic ray flux that reaches Earth. The heliosphere does not block all cosmic rays, but it attenuates them significantly. It carves out a protected region of space within which the planets orbit, buffered from the full intensity of what lies beyond. The boundary of this protective bubble is not a simple line. Scientists recognized that the transition from the sun's domain to interstellar space would involve several distinct structures, each marking a different stage in the handover from one environment to the other. The first structure is the termination shock. The solar wind flows outward supersonically, faster than the speed at which pressure waves can travel through the plasma. When a supersonic flow meets an obstacle, it cannot slow down gradually. It slows abruptly in a thin region where energy is rapidly transferred and the plasma heats up, compresses, and becomes turbulent. This abrupt transition is a shock wave. For the solar wind, the obstacle is the pressure of the interstellar medium, and the resulting boundary is the termination shock. Models predicted it would be located somewhere between roughly 75 and 90 astronomical units from the Sun, between roughly 7 and 8 billion miles out, though the exact distance would shift somewhat depending on the strength of the solar wind at any given time. Beyond the termination shock, the solar wind does not stop. It slows to subsonic speeds, heats up, and enters a region of turbulent, compressed plasma that scientists call the heliosheath. This is not yet interstellar space. It is a transition zone, a thick, churning shell of slowed solar material pressed up against the interstellar medium, piling up the way water thickens and swirls ahead of a moving hull. Within the heliosheath, particles travel in complicated paths. Magnetic field lines tangle and compress. The environment is disordered, caught between two domains, belonging fully to neither. It was expected to be broad, messy, and difficult to characterize cleanly. At the outer edge of the heliosheath lies the heliopause. The heliopause is the boundary scientist pointed to when asked where the solar system ends. Not in the sense of where the planets stop. Neptune is far closer in, but in the sense of where the sun's direct plasma influence finally gives way to the surrounding galaxy. At the heliopause, the pressure of the solar wind exactly balances the pressure of the interstellar medium. The invisible river of solar particles can push no farther. The interstellar medium can press no closer. It is an equilibrium, a stalemate written in plasma physics, maintained by the continuous balance of two opposing forces. Beyond the heliopause in the models was true interstellar space. The solar wind would be absent. The sun's magnetic field, stretched and thinned across billions of miles, would give way to the galactic magnetic field. Cosmic ray levels would be higher, the shielding of the heliosphere left behind. Solar particles would be essentially undetectable. The environment would be defined not by our star, but by the galaxy. The model scientists had assembled by the late 20th century was coherent and well-reasoned. It was not speculation. It was built from direct measurements of the solar wind, taken by spacecraft near Earth, theoretical work on plasma physics and magnetohydrodynamics developed over decades, and observational estimates of the interstellar medium's density and pressure drawn from astronomical data. The termination shock, the heliosheath, the heliopause. These were not invented structures. They followed from the physics with a kind of internal logic that made the overall picture feel reliable, and in its broad architecture, it was reliable. The general sequence of structures the models described, shock, turbulent sheath, final boundary, turned out to be real. Voyager would eventually confirm their existence, but the model had limits that no one could fully see from the inside. It was built without direct measurements of the region it was describing. Everything beyond a few astronomical units from the Sun was inferred, estimated, extrapolated. The density of the interstellar medium in our specific local neighborhood was not precisely known. The exact strength and orientation of the local interstellar magnetic field was uncertain. The way the Sun's magnetic field and the galactic magnetic field would interact at the boundary had been modeled with reasonable assumptions, but assumptions nonetheless. The predicted distance to the termination shock and heliopause rested on values plugged into equations, values that were the best available estimates, not confirmed measurements. The model was elegant. It was physically honest. It made clear, testable predictions, but no spacecraft had ever traveled far enough to test them. The termination shock had never been crossed. The heliosheath had never been sampled. The heliopause had never been measured from the inside. Everything scientists believed about the edge of the solar system in the 1980s and 1990s was, in the strictest sense, still theoretical, a well-supported theory, a reasonable theory, but a theory waiting for something to arrive and check its work. Voyager was still traveling outward. The power was still holding. The signals were still coming, and the edge, when the spacecraft finally reached it, was not where the models had placed it. For 27 years, Voyager 1 traveled outward without crossing anything that could be called a boundary. It passed Jupiter in 1979. It passed Saturn in 1980. It swung past Titan, bent its trajectory upward out of the plane of the solar system, and kept going. Year after year, the signal kept coming. The instruments kept measuring. The solar wind kept flowing around the spacecraft, still detectable, still present, still carrying the sun's particles outward into the darkness. The termination shock, where the solar wind would abruptly slow from supersonic to subsonic speeds, had not yet appeared. Many estimates had placed the termination shock somewhere between 75 and 90 astronomical units from the Sun. Predictions varied, partly because the boundary was expected to shift with solar activity and direction, but Voyager 1 passed 75 astronomical units, then 80, then 85. The solar wind was still supersonic. The termination shock had not been crossed. Something was farther out than expected. The question was how much farther? The answer came in 2004. In late 2003 and into 2004, the instruments aboard Voyager 1 began registering changes. The intensity of low-energy particles increased. The magnetic field showed signs of compression. The behavior of the plasma around the spacecraft was shifting in ways consistent with an approach to the termination shock. The data, when it arrived at Earth after a journey of more than 14 hours at the speed of light, told scientists that Voyager 1 was finally nearing the first major boundary in 2004 at a distance of approximately 94 astronomical units from the Sun, roughly 7 billion miles. Voyager 1 crossed the termination shock. The solar wind slowed. The plasma heated and compressed. The particles that had been streaming outward at hundreds of kilometers per second were abruptly reduced to subsonic speeds. The crossing was real, and it was measurable. The termination shock existed with the structure and character the model had described. But it was not where many estimates had suggested it would be. It was billions of miles farther out. Voyager 1 had traveled 94 astronomical units before the solar wind finally slowed at that first great transition. Some estimates had placed the near edge of the expected range at around 75 astronomical units. The termination shock appeared nearly 20 astronomical units beyond that, close to 2 billion miles farther than the lower end of what many models had suggested. But one measurement is not a full picture. One spacecraft crossing one boundary in one direction tells you something about one corridor of space. The heliosphere is a three-dimensional structure surrounding the Sun in all directions. To understand its true scale, scientists needed a second measurement from a different direction at a different time. 3 years later, they got it. Voyager 2 had taken a different path through the outer solar system. After its encounters with Uranus and Neptune, it continued outward in a direction below the plane of the solar system, a very different path from Voyager 1, which had been deflected upward by its Titan flyby. The two spacecraft were sampling the heliosphere from different angles, like two travelers crossing the same ocean at different latitudes and reporting back what each one found. In 2007, Voyager 2 crossed the termination shock at approximately 84 astronomical units from the Sun, 10 astronomical units closer than Voyager 1's crossing. Nearly a billion miles of difference, measured from the same central point in a different direction. This immediately told scientists something important. The termination shock was not a smooth, symmetric surface sitting at a fixed distance in all directions. The boundary was closer in one direction than in another. The heliosphere was already showing signs of an asymmetry that the simplest models had not fully captured. The interstellar medium pressing against the outer boundary was not pressing equally from all sides. The solar wind pushing outward was not uniform in strength across every direction. Differences in solar activity between the two crossing years may also have contributed to the gap. The edge was real, but it was not uniform. The termination shock, however, is not the final boundary. It is the first major transition, the place where the solar wind slows dramatically but does not stop. Beyond it lies the heliosheath, the thick and turbulent region of slowed, compressed solar plasma pressing against the interstellar medium. And beyond that lies the heliopause, the true plasma boundary where solar wind particles finally give way entirely to the interstellar environment. That is the crossing that defines where the Sun's domain genuinely ends. Reaching it would take years more. After crossing the termination shock, both spacecraft spent years traveling through the heliosheath. The boundary was still far. The signal was still coming, but growing slower to decode as the power faded, and the teams managing the spacecraft made careful decisions about which instruments to keep running. Years passed. The spacecraft kept moving at roughly 35,000 to 38,000 miles per hour, fast by any human standard, slow against the scale of what they were crossing. Predictions for the heliopause varied widely. Some older estimates had placed it closer to about 90 to 110 astronomical units, based on assumptions about the pressure of the local interstellar medium that had not yet been tested directly. Other models allowed for a considerably larger heliosphere, depending on what values were assumed for solar wind strength and interstellar conditions. The range of predictions was broad, and the uncertainty was real. Not in the summer of 2012, something changed in the data from Voyager 1. The levels of solar energetic particles, the charged particles originating from the sun, dropped sharply, almost to zero, within days. The cosmic ray intensity, those high-energy particles streaming in from the galaxy, rose sharply at nearly the same moment. The magnetic field measurements shifted. The environment around the spacecraft had changed in a way consistent with crossing the heliopause. Solar particles on one side, galactic particles on the other, a threshold between two fundamentally different regimes. In August 2012, at a distance of approximately 121 astronomical units from the Sun, roughly 2 billion miles, Voyager 1 crossed the heliopause. It entered interstellar space. The confirmation took time. Scientists studied the data carefully over the following months, checking it against models and debating its interpretation. The magnetic field behavior at the crossing raised questions that would take years to fully address, a point that belongs to a later chapter. But on the fundamental question, had Voyager 1 left the solar wind behind, the evidence was clear. The solar particles were gone. The galactic cosmic rays were present at levels consistent with interstellar space, at 121 astronomical units. Voyager 1's crossing showed that the larger end of the predicted range was closer to reality. The estimates that had placed the heliopause near 90 to 110 astronomicals were too conservative. The heliosphere was bigger than those models had assumed, and the crossing data gave scientists something they had never had before, a real, measured distance to work backward from. 6 years later, in 2018, Voyager 2 crossed the heliopause at approximately 119 astronomical units, remarkably close to Voyager 1's crossing distance, despite having approached from a different direction and during a different phase of the solar activity cycle. The near agreement of the two crossings, after the asymmetry seen at the termination shock, gave scientists a clearer picture of the heliopause's overall scale, while still leaving open questions about its detailed shape. What did it mean that the edge was farther away than many estimates had placed it? It meant that the sun's protective bubble was larger than those models had suggested. The balance point, where the outward pressure of the solar wind finally equaled the inward pressure of the interstellar medium, was farther from the sun than many equations had placed it. Part of the answer likely involved the local interstellar environment, its density, pressure, magnetic field, and the changing strength of the solar wind over the solar cycle. Each of those factors feeds into the pressure balance that determines where the heliopause sits, and each had been estimated rather than directly measured before Voyager arrived. Voyager, by traveling there and crossing the boundary, converted those estimates into data. The physics was sound, the scale was revised, but the distance was only the first surprise. Because once scientists absorbed the fact that the heliosphere was larger than many models had suggested, The next question became its shape. A larger bubble might still be a simple one, a sphere sitting at a corrected distance, symmetric and orderly. But Voyager would show that the heliosphere was something far less tidy than that. The shape of the sun's protective region turned out to be stranger, more asymmetric, and more complex than the cleanest models had predicted. And understanding that shape would require comparing what the two spacecraft found in two different directions at two different times, and confronting the possibility that the heliosphere looks nothing like a bubble at all. That is what Chapter 4 is about. The word bubble is useful. It gives the mind something to hold, a simple, rounded shape, symmetric in all directions. The sun at its center and the heliopause as its outer skin. For decades, this image served well enough as a shorthand for the heliosphere. Not because scientists believed the heliosphere was perfectly spherical, but because the broad models suggested it would be roughly so. Compressed slightly at the front, where the sun's motion through the interstellar medium pressed the boundary inward. Extended somewhat at the back, where the solar wind would push a long trailing region outward behind the sun's direction of travel. A teardrop, perhaps, an elongated sphere, something orderly, something that basic fluid dynamics could describe without too much difficulty. Voyager did not find something orderly. To understand why the shape of the heliosphere matters, it helps to think about what shapes it. The heliosphere is not a rigid container. It has no walls. Its boundary, the heliopause, exists only because two pressures are in balance: the outward pressure of the solar wind and the inward pressure of the interstellar medium. Change either pressure in any direction and the boundary shifts. The shape of the heliosphere at any given moment is a record of those pressures, a three-dimensional map of where the balance happens to fall. In every direction simultaneously, several forces pull that shape away from a simple sphere. The first is the sun's motion through the galaxy. Our solar system is not stationary. It moves through the local interstellar medium at roughly 26 kilometers per second relative to the surrounding gas. From the perspective of the heliosphere, this means the interstellar medium is flowing past, pressing harder against the leading face of the heliosphere, the direction toward which the sun is traveling, and less hard against the trailing side. Many models predicted this would compress the heliopause on the nose side and allow it to extend farther on the tail side, creating a shape more like a comet than a sphere, blunt at the front, elongated behind. The second force is the interstellar magnetic field. The gas between the stars carries a magnetic field, and that field does not simply flow around the heliosphere without effect. It presses against the boundary with its own pressure, and its orientation, the direction it points as it approaches the heliosphere, influences where the boundary is pushed inward and where it is left to expand. The interstellar magnetic field in our local neighborhood is not perfectly aligned with the sun's direction of motion, which means its pressure is not applied symmetrically. It bears against certain faces of the heliosphere more than others. The third factor is the solar wind itself, which is not uniform in all directions. The sun's equatorial regions tend to produce a slower, denser solar wind. The polar regions produce a faster, thinner wind. These variations mean the outward pressure that maintains the heliosphere's boundary is not the same in every direction. The boundary will be pushed farther out where the solar wind is stronger and pulled closer in where it is weaker. three asymmetric forces acting simultaneously on a boundary maintained by pressure alone. The result, many models suggested even before Voyager arrived, would be a shape that was more complex than a simple bubble. But how complex, and in which specific ways? That was a question that required data. Voyager 1 and Voyager 2 provided that data, imperfectly and partially. From two directions, Voyager 1 traveled outward above the plane of the solar system, sampling one high-latitude region of the heliosphere. Voyager 2 traveled below the plane in another high-latitude direction, sampling a different face of the structure entirely. The asymmetry terminate shock crossings, 94 astronomiclets for Voyager 1, 84 astronomiclets for Voyager 2, was the first concrete measurement of the heliosphere's non-uniformity. A difference of roughly 10 astronomical units, close to 1 billion miles, between two crossings in two different directions. Some of this difference could be attributed to the different times of crossing and different phases of the solar activity cycle, which affects solar wind pressure, but part of it reflected genuine directional differences in the heliosphere's structure when the heliopause crossings came. 121 astronomiclets for Voyager 1 in 2012, 119 astronomicals for Voyager 2 in 2018. The two distances were much closer together. That near agreement surprised some scientists who had expected the heliopause to show more dramatic directional variation at those locations, given the asymmetries seen at the termination shock. It suggested that the heliopause geometry, at least in the two directions sampled, was more similar than the termination shock data had implied, though the crossing conditions differed in important ways between the two spacecraft. What the Voyager data could not directly resolve was the shape of the heliosphere in directions the spacecraft never traveled. The long tail of the heliosphere, the region trailing behind the sun's direction of motion, where many models predicted an extended comet-like structure stretching for hundreds or even thousands of astronomical units, was beyond reach. No spacecraft has traveled in that direction far enough to measure it. Its shape remains, even today, a matter of modeling and indirect inference, rather than direct measurement. In the years after Voyager 1 entered interstellar space, a separate line of evidence began to reshape the picture further. NASA's Interstellar Boundary Explorer, a spacecraft known as IBEX, was launched in 2008. It does not travel to the edge of the heliosphere. It sits in Earth's orbit and detects a particular type of particle, energetic neutral atoms, that are created at the boundary between the solar wind and the interstellar medium, and then travel back inward in straight lines, carrying information about where they came from. By mapping the arrival directions of these particles, IBEX can construct an indirect image of the heliosphere's outer boundary from the inside. The images IBEX returned were unexpected. They showed a bright, narrow ribbon of energetic neutral atoms arcing across the sky, a feature that did not appear in most pre-existing models and whose origin required new theoretical work to explain. The ribbon appeared to be related to the direction and pressure of the interstellar magnetic field as it wraps around the heliosphere. It was a structural signature of the boundary, visible from the inside, that revealed information about the external magnetic pressure shaping the heliosphere from outside. The ribbon was not something Voyager detected directly, but it reinforced what Voyager's asymmetric crossings had already suggested. The heliosphere's shape is not a simple, smoothly elongated form. It is pushed, pulled, and sculpted by magnetic fields and pressure gradients that act differently in different directions. The bubble, as a mental image, was not wrong. It captured something true about the heliosphere, that it is a bounded region, carved out by the sun's outflow, sheltering the planets within. But as a precise description of the structure, it was incomplete. The heliosphere is asymmetric, magnetically shaped, and directionally dependent in ways that the simplest models had not fully anticipated. What Voyager contributed was not a complete map of that shape. Two spacecraft in two directions cannot map a three-dimensional structure, but a set of real measurements against which models could be tested and refined. The crossing distances told scientists something concrete about the size of the heliosphere in specific directions. The differences between those distances told them something about its asymmetry and the questions those differences raised. About the interstellar magnetic field, the solar wind's directional variation, the length and structure of the tail, became the foundation for a generation of new modeling work. The shape of the heliosphere is still being debated. New data, new models, and new observations continue to revise the picture. But it was Voyager that first made the shape a question that required real answers rather than comfortable assumptions. And once the shape was under revision, a third discovery followed. Because scientists had also assumed, in their broad model, that the boundary, wherever it was and whatever shape it took, was essentially stable. A fixed surface maintained by a steady balance of pressures. Voyager showed that the boundary was not fixed at all. A boundary maintained by pressure is not a rigid thing. This is worth sitting with for a moment. The heliopause and the termination shock exist not because anything solid holds them in place, but because two sets of forces happen to be equal at those locations. Outward pressure from the solar wind, inward pressure from the interstellar medium. When those pressures balance, the boundary holds. When one of them shifts, when the solar wind strengthens or weakens, when the interstellar medium's density changes, the balance point moves. The boundary moves with it. Scientists understood this in principle before Voyager crossed anything. The models included this variability. They expected the termination shock to move inward during solar minimum, when the sun's activity is quieter and the solar wind is somewhat weaker, and to move outward during solar maximum, when increased solar wind output pushes the boundary farther into space. They expected the heliopause to respond more slowly, buffered by the thick heliosheath between it and the solar wind's fluctuations. These were not controversial predictions. They followed logically from the physics. What the models did not fully anticipate was how dramatically, how quickly, and how measurably these movements could occur, and how much structure the moving boundary would reveal about the relationship between the sun's activity and the outermost edge of its domain. The solar cycle runs on roughly an 11-year rhythm. The sun moves from a period of relative quiet, solar minimum, when sunspots are few and the solar wind is comparatively steady, to a period of intense activity, solar maximum, when sunspots are numerous, solar flares are frequent, and the solar wind becomes stronger and more variable. This cycle has been observed and measured for centuries in the case of sunspots, and directly in the solar wind since the early days of space exploration near Earth. The effects of the solar cycle on the solar wind are measurable, but not dramatic in everyday terms. The solar wind's speed and density vary, but the overall outflow continues without interruption. The changes are a matter of degree. At the edge of the solar system, those changes in degree become changes in location. Voyager 2's crossing of the termination shock in 2007 offered a striking illustration of this. The spacecraft did not cross the termination shock once cleanly and continue onward. It crossed it multiple times. The boundary swept back and forth across the spacecraft's position as varying conditions in the solar wind caused the termination shock to move inward and outward. Voyager 2 measured itself on one side of the boundary, then the other, then back again, as the shock oscillated around it before the spacecraft finally moved far enough outward to leave it definitively behind. This multiple crossing was not predicted with any specificity. The models knew the boundary moved. They did not fully capture how rapidly and repeatedly it could sweep past a given location. The termination shock, it turned out, was not a wall that a spacecraft passed through once and left behind. It was a dynamic surface, responsive to changes in solar wind pressure that had originated at the Sun months earlier and traveled outward across billions of miles before reaching the boundary and pushing it in one direction or the other. The time delay is part of what makes this striking. A solar wind pressure pulse that leaves the Sun today will take roughly 1 year to reach the termination shock at around 84 to 94 astronomical units. By the time it arrives, the Sun may be in a completely different phase of its activity. The boundary at the edge of the solar system is responding to conditions that existed at the Sun a year earlier. It carries, in its position, a kind of delayed record of the Sun's past behavior, the heliosheath. That turbulent region between the termination shock and the heliopause also showed unexpected dynamism. As Voyager 1 traveled through the heliosheath between its 2004 termination shock crossing and its 2012 heliopause crossing, it spent 8 years in a region that the models had described in general terms, but never directly sampled. The data it returned painted a picture of a region that was not simply a gradual transition zone. Particle intensities in the heliosheath fluctuated. The magnetic field showed variations on scales that suggested structure and turbulence more complex than a smoothly compressed shell. Streams of particles moving in unexpected directions hinted at flows within the heliosheath that were not easily explained by the simplest models. The region was dynamic in ways that suggested the heliosheath was not merely a passive buffer zone, but an actively evolving environment responding continuously to conditions on both sides of it. At the outer edge, the heliopause itself showed signs of variability as well. The data around Voyager 1's crossing in 2012 suggested that the boundary was not a perfectly stable surface at the moment of crossing. Fluctuations in particle levels in the months surrounding the crossing hinted at a boundary that was oscillating, presenting Voyager with a more complex transition than a single clean step from one environment to the other. The motion of the boundary is sometimes described metaphorically as breathing. The heliosphere expanding and contracting with the Sun's activity cycle, inhaling slightly during solar minimum and exhaling outward during solar maximum. It is a useful image, and it captures something true. The boundary responds to the Sun's rhythm over years and decades. expanding and contracting in response to changes in solar wind pressure that originate at the sun and propagate outward at the speed of the solar wind. But it is a metaphor, not a mechanism. The boundary does not breathe. It moves because pressure changes, and pressure changes because the sun's activity changes, and that activity propagates outward across billions of miles until it reaches the balance point and shifts it. The motion is real. The physics behind it is not mysterious. What Voyager revealed was the degree to which that motion was measurable, detectable, and structurally informative, more so than many models had suggested. The significance of a moving boundary reaches beyond the mechanics of the heliosphere itself. If the boundary moves, it means the level of protection the heliosphere provides to the inner solar system changes over time. During periods of solar minimum, when the termination shock retreats somewhat, galactic cosmic rays may penetrate slightly deeper into the heliosphere before being deflected. The shielding is not constant. It pulses with the sun's activity, offering slightly more protection at some times and slightly less at others, over much longer timescales, millions of years. The sun moves through different regions of the galaxy, with different interstellar medium densities and pressures. When the solar system passes through a denser region of the interstellar medium, the heliosphere would be compressed significantly, potentially allowing more cosmic radiation to reach the inner solar system. When the solar system moves through a thinner region, the heliosphere expands. The current position of our solar system within the low-density local bubble may mean that the heliosphere is presently larger and more protective than it has been at many other times in Earth's history. These are long timescale questions that Voyager cannot answer directly. But by revealing that the boundary is dynamic at short timescales, moving in response to the 11-year solar cycle and to individual solar wind pressure pulses, Voyager pointed toward a more general truth. The edge of the solar system is not a fixed feature of the landscape. It is a responsive, continuously adjusting surface shaped by forces on both sides of it. The boundary moved, it shifted, it swept back and forth across Voyager's instruments and left a record in the data. And within that moving, dynamic boundary region, the data revealed something else entirely. Something that did not appear in the models at all. A structure inside the heliosheath that no one had predicted. A channel where particles were being accelerated and directed in ways that required an entirely new name. Scientists would eventually call it the magnetic highway, and it is where we are going next. In the years between Voyager 1's crossing of the termination shock in 2004 and its eventual crossing of the heliopause in 2012, the spacecraft traveled through the heliosheath, that thick, turbulent shell of slowed solar plasma, pressing outward against the interstellar medium. 8 years of transit through a region no instrument had sampled before. 8 years of data flowing back across more than 10 billion miles. Arriving at Earth so faint, it required the full sensitivity of the deep space network to hear. For most of that transit, the instruments told a consistent story. Solar energetic particles were present. Galactic cosmic rays were present, but partially attenuated, blocked to some degree by the heliosphere's outer layers. The magnetic field was tangled and compressed, as the models had suggested the heliosheath would be. The environment was disordered, as expected for a region caught between two domains. Then, in 2012, something changed. and it changed in a way that did not fit cleanly into any prepared category. Beginning in the latter half of 2011 and accelerating through mid-2012, Voyager 1's instruments began registering a pattern that puzzled the scientists watching the data. The intensity of solar energetic particles, those originating from the sun and its activity, began dropping, not gradually, not slowly, but in a series of sharp, step-like decreases. Meanwhile, the flux of galactic cosmic rays, high-energy particles streaming in from outside the solar system, began rising, also in steps, also sharply. This was in broad outline, consistent with what scientists expected to see near the heliopause. Beyond the heliopause, solar particles should fade, and galactic cosmic rays should be more abundant. The data pattern looked like an approach to the boundary, or perhaps even a crossing of it, but there was a complication. The magnetic field was not behaving the way most models predicted it should at the heliopause. The direction of the magnetic field, the orientation of its lines in space, had not changed significantly. Many models had expected a noticeable rotation in field direction at the heliopause, where the sun's outward spiraling magnetic field would give way to the differently oriented galactic magnetic field. That rotation was not clearly visible in Voyager 1's data during the period when the particle levels were changing so dramatically. This created genuine uncertainty. The particle data said one thing. The magnetic field data said something less clear. What the instruments were detecting, scientists eventually concluded, was a distinct structure within the boundary region, a region where the geometry of the magnetic field lines created something like open channels or pathways running roughly parallel to the heliopause surface. Along these pathways, solar particles could stream outward and escape the heliosphere, while galactic particles could stream inward. The magnetic field lines in this region were not tangled and turbulent, as they had been deeper in the heliosheath. They were relatively ordered, oriented in a direction that connected the interior of the heliosphere to the space beyond it. Scientists called this structure the magnetic highway. The name is descriptive rather than technical. What it refers to is a region where the topology of the magnetic field, the way its lines are arranged in space, allows particles of different origins to travel along those lines in opposite directions simultaneously. Solar particles moving outward along the field lines, galactic particles moving inward along the same lines, both following the path that magnetic geometry offered them. In this region, the usual shielding effect of the heliosphere was reduced. The barrier between the solar environment and interstellar space was not a wall, but a permeable mesh, at least in terms of particle transport. Particles from outside could penetrate inward along the highway. Particles from inside could escape outward. This was not entirely without precedent in plasma physics. Magnetic reconnection, the process by which magnetic field lines from different regions break and reconnect, is known to create pathways for particle transport in other contexts, including at Earth's own magnetopause. But finding such a structured, extensive region of open field lines at the outer boundary of the heliosphere, in a configuration that allowed the observed particle fluxes, was not something the models had specifically anticipated in this form. The magnetic highway region complicated the picture of the heliopause as a clean, distinct boundary. Within it, the usual markers, that scientists plan to use for identifying a heliopause crossing. Solar particles dropping, galactic particles rising, were already changing, even though the spacecraft had not yet fully crossed into interstellar space. The boundary was not presenting itself as a single threshold. It was a layered, structured transition with at least one distinct internal feature that had its own measurable character. For several months in 2012, scientists debated what Voyager 1 was actually measuring. Was it inside the heliosphere or outside? Had it crossed the heliopause, or was it still in the magnetic highway region? The particle data kept evolving. The magnetic field data remained ambiguous. The picture was not resolving cleanly into any prepared category. Then, in August 2012, the solar particle levels dropped essentially to zero. The galactic cosmic ray levels reached values consistent with open interstellar space. The spacecraft had crossed the heliopause, but the crossing had been preceded and complicated by the magnetic highway, a structure that had no clear name or description in the models that existed before Voyager found it there. Quote, "The magnetic highway is one of the more conceptually striking of Voyager's discoveries, partly because it is so difficult to visualize. It is not a road, it is not a tube, it is a region of space where the geometry of an invisible field creates preferred directions for particle motion, where the landscape of the magnetic field, rather than any physical structure, shapes how matter moves. It exists at the edge of the heliosphere, in the region where the sun's magnetic influence and the galaxy's magnetic influence are closest to one another, and it is a direct consequence of the interaction between those two fields. That interaction, it turned out, had depth and structure that the simplest models had not captured. The magnetic highway was one expression of that complexity. The behavior of the magnetic field, that the crossing itself was another, a discovery that would eventually require Voyager 2's crossing 6 years later to add meaningful context. But before the magnetic field story could be resolved, Voyager 1 had already passed through the heliopause and entered a region that no spacecraft had ever sampled, and what it found there raised its own quiet set of surprises. Because the space beyond the boundary, the true interstellar medium, the substance of the galaxy itself between the stars, was not the empty darkness the name suggested. It had structure, it had density, it had a field running through it. It was extremely thin by any measure that matters to human experience. But it was not nothing. Beyond the heliopause, the solar wind is absent. The particles that have streamed outward from the sun for billions of years. The continuous invisible river of plasma that fills the heliosphere and shapes its environment do not cross the heliopause in any significant quantity. They are deflected and turned away at the boundary, compressed into the heliosheath and redirected. On the other side, in true interstellar space, the sun's direct outflow is not present. This was expected. It was one of the defining predictions of the model, and Voyager's measurements confirmed it. After crossing the heliopause in August 2012, Voyager 1's plasma instruments registered the absence of solar wind particles with remarkable clarity. That signal, the solar wind, simply stopped. What was not absent was everything else. The interstellar medium, even in the relatively quiet neighborhood of space through which our solar system currently moves, is not a perfect vacuum. It is, by any practical measure, extraordinarily thin. The electron density that Voyager 1 encountered just beyond the heliopause was on the order of 0.08 electrons per cubic centimeter, roughly 80 thousandths of an electron per cubic centimeter. For comparison, the solar wind near Earth carries a plasma density of around 5 to 10 particles per cubic centimeter. The interstellar plasma Voyager entered was thinner than the solar wind by a factor of roughly 100, but it was there, and it had properties. The plasma beyond the heliopause carried a magnetic field, the galactic magnetic field, organized on scales far exceeding anything associated with the Sun. It carried galactic cosmic rays streaming through interstellar space at high energies in all directions continuously. It had a temperature extremely high in electron volt terms, though at such low densities, the concept of temperature connects only loosely to any intuitive sense of heat. And it had, as Voyager's instruments would reveal over the following months and years, a capacity to respond to disturbances with coherent, measurable waves. The instrument that made some of the most precise measurements of the interstellar medium's properties was not designed primarily for that purpose. The plasma wave science instrument aboard Voyager 1 detects oscillations in the electric field around the spacecraft, waves propagating through whatever plasma the spacecraft is moving through. In the heliosphere, this instrument had been used for decades to study plasma conditions closer to the Sun. Beyond the heliopause, it found something unexpected. The interstellar plasma oscillated in response to certain events, and those oscillations could be used to infer the density of the plasma through which Voyager was traveling. The density inferred from these plasma wave measurements, around 0.08 electrons per cubic centimeter, was consistent with independent estimates of the local interstellar medium's electron density, derived from astronomical observations of distant pulsars and other sources. The agreement between Voyager's direct measurements and the indirect astronomical estimates was in itself a form of confirmation. Two completely different methods applied to the same region of space, producing consistent answers. The plasma waves detected by Voyager 1 in interstellar space had a character that was both scientifically informative and, in a quieter sense, evocative. They were oscillations in the electron density of the interstellar medium, ripples propagating through an extremely thin plasma at speeds determined by the plasma's own properties. They were not sound waves. They were not electromagnetic waves in the usual radio sense. They were plasma oscillations, a phenomenon that occurs when electrons in an ionized gas are displaced and then respond to their own electromagnetic interactions, creating a wave that propagates through the medium. These oscillations, translated into audio frequencies for public presentation, produce a tone, a kind of hum emerging from the structure of the interstellar medium itself. The plasma of interstellar space, when disturbed, responds with a coherent vibration. That vibration has a pitch that reflects the plasma's density. It is a measurement, it is a precise physical observation, but it is also, in some difficult to articulate way, a voice from the medium between the stars, a signal produced not by any machine, but by the fabric of interstellar space, responding to a disturbance passing through it. Beyond the plasma, the interstellar medium carried a magnetic field, whose direction and strength Voyager's magnetometer could measure directly. The field was present, coherent, and oriented in a specific direction, not randomly arranged, not chaotic, but organized on scales that reflected the large-scale structure of the local galactic environment. The field lines ran in a direction that was consistent with, though not perfectly matching, the orientation suggested by earlier astronomical observations. The cosmic ray environment beyond the heliopause was also measurably different from what Voyager had experienced inside the heliosphere. Within the heliosphere, the solar wind's pressure had partially deflected and attenuated the galactic cosmic ray flux. Beyond the heliopause, that deflection was absent. The cosmic ray intensity rose to levels consistent with the unshielded interstellar environment, not dramatically higher than in the heliosheath. The heliosphere shielding had been partial, not total, but measurably, consistently elevated. What these measurements collectively described was a medium that was genuinely thin by almost any standard, but that was nevertheless a physical substance with structure, fields, density, and dynamics. The space between the stars in the region Voyager entered was not a void in any strict sense. It was an environment, an extremely dilute one, occupying a scale of distance that makes any human intuition about thinness feel inadequate, but an environment with measurable properties that connected it to the broader structure of the galaxy. This distinction between a void and an extremely thin structured medium matters for understanding how the galaxy works. The interstellar medium is the material from which stars form. It is the medium through which supernova shockwaves propagate. It carries the galactic magnetic field that influences how cosmic rays travel through the galaxy. It is the substance that the heliosphere pushes against. It is, in a real sense, the ocean through which our solar system swims. Voyager, by crossing into it, became the first instrument to measure that ocean directly from the inside at the specific location where our solar system currently resides. The measurements it returned: plasma density, magnetic field strength and direction, cosmic ray flux, plasma wave properties, gave scientists a local sample of the interstellar medium that no telescope observation from within the heliosphere could have provided. The medium was thin, it was quiet, but it was not empty, and of all the properties Voyager measured beyond the heliopause, one in particular had been the subject of specific and confident prediction, a prediction that the data did not straightforwardly confirm. The magnetic field at the crossing and the direction it pointed in interstellar space raised questions that would take years and a second crossing to begin to resolve. That is the story of Discovery 6. Magnetic fields have direction. This is not a trivial statement. A magnetic field at any given point in space points somewhere. It has a strength and it has an orientation. The field lines that thread through the heliosphere point in directions shaped by the sun's rotation, the solar wind's outward flow, and the interplay of forces within the heliospheric current sheet. The field lines that thread through the interstellar medium outside the heliosphere point in directions shaped by the large-scale structure of the galaxy and the local history of the interstellar environment through which our solar system moves. Through these two fields, the heliospheric and the interstellar, are not the same. They originate from different sources. They have been shaped by different forces acting over different timescales. Where they meet, at and near the heliopause, models predicted they would be oriented differently. A spacecraft crossing the heliopause should, in principle, detect a change in the direction of the magnetic field. A rotation, a shift in the angle the field lines make with respect to the spacecraft's orientation. This was one of the clearest, most specific predictions associated with heliopause crossing. The solar magnetic field and the interstellar magnetic field were expected to point in different directions. The crossing should be visible in the magnetometer data. When Voyager 1 crossed the heliopause in August 2012, the magnetometer data did not show this expected rotation clearly. How might the magnetic field direction? Voyager 1 measured just inside the heliopause, and just outside it were surprisingly similar. The field did not make the turn that many models had predicted. Its orientation in the interstellar medium, at least in the region immediately beyond the heliopause, was closer to the orientation in the heliosheath than the models had suggested it should be. This created immediate and genuine debate within the scientific community. On one side, the particle data was unambiguous. Solar energetic particles had dropped to near zero. Galactic cosmic rays, cosmics had reached levels consistent with interstellar space. These were the signatures that defined the crossing, and they were clear. The spacecraft had entered a region dominated by galactic particles, not solar particles. On the other side, the magnetic field data was puzzling. If the field direction had not rotated at the crossing, did that mean the models were wrong about the interstellar field's orientation? Or did it mean Voyager 1 had not yet fully exited the heliosphere's magnetic influence? Or did it mean something else entirely about how the interstellar magnetic field behaves near the heliopause? Some scientists proposed that the local interstellar magnetic field near the heliopause might be draped around the outside of the heliosphere, bent and shaped by the pressure of the heliosphere pushing outward against it, the way a river's current is deflected around a large rock. If the interstellar field lines were draped in this way, they might run roughly parallel to the heliopause surface in the immediate vicinity of the crossing, producing an orientation that appeared similar to the field inside the heliosphere, even though the field's origin was entirely external. Moving farther from the heliopause in this picture would eventually bring Voyager into a region where the interstellar field's undisturbed orientation became apparent. This hypothesis, magnetic draping, had precedent in other planetary environments where magnetic obstacles deflect external fields. It was physically reasonable, and it offered a way to reconcile the particle data, which clearly indicated heliopause crossing, with the magnetic data, which did not show the expected rotation at the moment of that crossing. The question remained somewhat open until Voyager 2 crossed the heliopause in November 2018. Voyager 2 carried a functioning plasma science instrument that Voyager 1's had stopped returning useful data from decades earlier. This gave Voyager 2 a direct plasma measurement capability at the crossing that Voyager 1 had lacked. The plasma data from Voyager 2's crossing was clear and direct. The solar wind plasma dropped to essentially undetectable levels at the heliopause, and the plasma density beyond it matched interstellar values. The magnetic field data from Voyager 2's crossing showed a clearer change in field direction than Voyager 1 had detected. Though still not as dramatic a rotation as the simplest models had predicted. The field shifted, it changed. The change was consistent with a crossing from heliospheric field to interstellar field. Transit, But the transition was subtle enough that it reinforced the idea that the interstellar magnetic field near the heliopause was influenced by the presence of the heliosphere itself, bent and oriented partially by the same pressure interaction that shaped the heliosheath on the inside. Together, the two crossings painted a picture that was more nuanced than the original prediction. The magnetic field does change at the heliopause, but the change is smaller than many models expected, and the local interstellar field in the immediate vicinity of the crossing appears to be shaped by its proximity to the heliosphere, draped, deflected, and oriented partly in response to the obstacle it surrounds. This is a refinement, not a contradiction. The models correctly identified that the two fields would differ. The models correctly predicted that a change would occur. What they underestimated was the degree to which the interstellar field near the boundary would itself be influenced by the heliosphere's presence, the degree to which the two environments would affect each other across the boundary, rather than simply sitting on opposite sides of a clean dividing line. The magnetic field, like the shape of the heliosphere and the distance to its edge, turned out to be more complex in the details than the broad model had anticipated. But even after the crossing, after the solar wind had faded and the interstellar plasma had been measured and the magnetic field had been compared against predictions, one more surprise was waiting. Because the sun, even after its direct plasma influence had been left behind, had not entirely lost the ability to make itself felt in the space beyond its own boundary, its storms could still send echoes into the interstellar medium, and Voyager was there to hear them. None of the sun's direct reach ends at the heliopause. The solar wind, that continuous outward stream of plasma and magnetic field, is stopped at the boundary and does not continue into interstellar space in any significant form. Beyond the heliopause, the environment is shaped by the galaxy, not by the sun. The plasma Voyager moves through beyond the boundary, originates from stellar winds and supernova remnants distributed across the galactic neighborhood, not from our own star. The magnetic field threading that space is the galactic field, not the solar field stretched and wound into its characteristic spiral pattern. In that direct and continuous sense, the sun's influence ends at the heliopause. This is, in broad terms, what the models predicted, and it is what Voyager's measurements confirmed. But the sun does not always express itself through steady, continuous outflow. It also erupts. Periodically, and particularly near solar maximum, the sun releases enormous bursts of energy and plasma. A solar flare produces a sudden, intense brightening across a broad range of wavelengths. A coronal mass ejection sends billions of tons of magnetized plasma outward from the solar corona at speeds that can exceed 1,000 kilometers per second, much faster than the ordinary solar wind. These events send pressure pulses outward through the heliosphere, disturbances that travel with and through the solar wind, compressing the plasma ahead of them, enhancing the magnetic field, and eventually reaching the termination shock and heliosheath with enough residual energy to interact with the structure of the outer heliosphere. The journey is not fast by human standards. A pressure pulse from a major solar event, traveling at elevated solar wind speeds, takes roughly a year to reach the termination shock. By the time it reaches the heliopause, the transit time has stretched to more than a year, sometimes several years depending on the event's timing and the distance it must travel. What Voyager 1 encountered beyond the heliopause was, in some cases, the result of solar activity that had occurred years before the detection. This time delay gives the heliosphere a kind of memory. The outer regions of the solar system carry, encoded in the state of their plasma and magnetic fields, a record of events that happened much closer to the sun months or years earlier. The boundary and the space beyond it are not simply responding to the sun's current output. They are responding to its history. After Voyager 1 crossed the heliopause in 2012 and entered interstellar space, the spacecraft's plasma wave science instrument began detecting something unexpected. In 2013, it measured oscillations in the local electron plasma, coherent vibrations propagating through the interstellar medium beyond the heliopause. The frequency of these oscillations was directly related to the density of the plasma, allowing scientists to use them as a precise measurement tool for characterizing the interstellar environment. But the oscillations were not spontaneous. They were triggered. Their timing was traced back to a series of powerful coronal mass ejections from the sun that had occurred in 2012. Those ejections had sent pressure pulses outward through the solar wind, across the heliosphere, and through the heliopause. On the other side of the heliopause, the pressure disturbance did not simply vanish. It interacted with the interstellar plasma, compressing it slightly and exciting plasma wave oscillations that propagated through the medium and were detectable by Voyager's instruments. A similar event occurred in 2014 and 2015, again traceable to solar activity that had originated years earlier and whose disturbance had propagated outward through and beyond the heliopause to reach Voyager's instruments in interstellar space. The sun's direct plasma outflow does not cross the heliopause, but pressure disturbances from large solar events can propagate through the heliopause and produce measurable signatures in the interstellar medium on the other side. The boundary is not a perfect insulator. It is a dynamic interface, and large enough disturbances on one side can produce effects, however attenuated. On the other, this finding does not mean the sun controls the interstellar medium. It does not mean the heliosphere is ineffective as a boundary. The plasma beyond the heliopause is interstellar in origin and character. The cosmic ray environment there reflects galactic conditions, not solar ones. The magnetic field is the galactic field. None of those fundamental characterizations changed because of the plasma wave events. What the discovery revealed is that the heliopause is a permeable interface under the right conditions, and that the effects of very large solar disturbances can be detected as far out as Voyager 1's position in the interstellar medium. The boundary separates the two environments, but does not completely isolate them. Large events can couple energy across it in the form of pressure waves that propagate through the interstellar plasma and produce detectable oscillations. For scientists, the plasma wave measurements had an additional value beyond demonstrating this coupling. The frequency of the oscillations provided the most direct measurement yet of the interstellar plasma density. In the region Voyager was traversing, the density inferred from the oscillations, around 0.08 electrons per cubic centimeter, was consistent across multiple events, confirming that the interstellar medium through which Voyager moved had a relatively uniform electron density at that location. It was a precise measurement extracted from an indirect signal derived from the echo of a storm that had begun at the sun years before. 7 discoveries. Each one arrived quietly, in data transmitted across billions of miles at the speed of light, reduced to numbers by antennas the size of small buildings, interpreted by scientists who had spent careers preparing for measurements that no prior instrument had ever made. The boundary was farther than expected. Its shape was more complex than a simple bubble. It moved in response to the sun's own rhythm. It contained internal structures, the magnetic highway that models had not predicted. The interstellar space beyond it was not empty. The magnetic field at the crossing did not rotate as clearly as expected, and the sun's most violent events could still reach beyond the boundary and leave echoes in the space between the stars. 7 corrections to a model that had been built carefully, honestly, and with the best available data, a model that was right in its broad outlines and wrong in ways that only direct measurement could reveal. 2 spacecraft carried those measurements home, year after year, decade after decade. From a place no human instrument had ever been, they are still out there now. And they carry something with them that has nothing to do with plasma physics or magnetic fields. Something that was placed aboard before the spacecraft were launched. Something that was meant not for scientists, but for anyone who might someday find these objects drifting through the darkness. Before Voyager 1 was sealed and sent in 1977, a 12-inch gold-plated copper disc was bolted to its exterior. The same was done for Voyager 2. Each disc is contained in a protective aluminum jacket. On the outside of the jacket are engraved instructions, diagrams, not words, because no language could be assumed. The diagrams indicate how to construct a device that can play the record, what speed to play it at, and how to decode the images encoded within. They include a pulsar map, a diagram of 14 pulsars, and their rotational frequencies, arranged to indicate the position of our solar system within the galaxy at the time of the spacecraft's launch. For any civilization with sufficient scientific knowledge, the map provides both a location and a timestamp. The record is called the Golden Record. It was conceived and assembled in a period of weeks in 1977 under the direction of a small committee led by the astronomer and writer Carl Sagan. The committee faced a question that has no clean answer. If you could send one message from Earth to the cosmos, and you had only a few weeks to compose it, what would you say? What they assembled was not a summary of human knowledge. It was not a scientific report or a diplomatic communique. It was something closer to a portrait, an attempt to convey in sound and image something of what it is like to be alive on this particular planet. The Golden Record opens with greetings, 55 languages, a few words each. Hello, greetings, peace, we wish you well, spoken by speakers ranging across human linguistic diversity. The voices are brief and varied. They do not convey information in any technical sense. They convey presence, they say. There are beings here, and they have many ways of speaking to one another, and they wanted you to hear some of them. After the greetings come sounds, not music yet, sounds, the natural sounds of Earth, rain falling on leaves, wind moving through a field, surf breaking on a shore, the calls of birds and whales and insects, the beat of a human heart, a mother speaking softly to a child. These were chosen not for scientific content, but for texture, to give whatever listener might eventually decode the record some sense of the acoustic environment in which human life evolved, the sounds of the world that made us, then music, 90 minutes of it, drawn from across human cultures and across centuries. Bach and Beethoven, representing the Western classical tradition, Blind Willie Johnson, playing dark blues on an acoustic guitar, Georgian polyphonic chanting, a Pygmy Girl's initiation song, panpipes from the Solomon Islands, the Navajo night chant, Chuck Berry's Johnny B. Good, Louis Armstrong, Azerbaijani folk music, a Peruvian wedding song, a Japanese shakuhachi piece. Music from places and traditions that would never otherwise share a playlist, gathered together because each one said something true about the species that made it. The musical selections were argued over, refined, reconsidered. Some things that were proposed did not make the final cut. Other things were included because they seemed, in the committee's judgment, to represent not just a culture, but something more fundamental. The human capacity to organize sound into meaning, to express grief and joy, and longing and celebration through a structured arrangement of vibrations in air. The record also contains images, 116 of them, encoded as analog signals in a format that the jacket's instructions explain how to decode. The images show Earth from space. They show the sun and the planets. They show the diversity of human faces, bodies, and activities. They show children playing, people eating, a family gathered around a dinner table. They show a supermarket and a city at night. They show an astronaut in space and a woman licking an ice cream cone. They show DNA's structure and diagrams of human anatomy. They show a page of music and a school classroom. They show what a human being is and how human beings live, insofar as 116 images can do that. The record was not designed for scientific communication. It was designed for wonder. Carl Sagan understood that the probability of the golden record ever being found was essentially negligible. The spacecraft do not fly toward any particular star. They drift in the directions their final trajectories happen to send them. And the galaxy is so vast, and the distances between stars so enormous, and the time required to traverse those distances so incomprehensibly long, that finding these small metal objects in the darkness would require an improbability stacked upon an improbability. Voyager 1 will not make a close approach to another star system for roughly 40,000 years. It will pass within about 1.5 light years of a faint red dwarf star called Gliese 445. 1.5 light years is still an immense distance, close only in galactic terms. The record was sent anyway, not because it was likely to be received, but because sending it was itself meaningful, an act that said something about the civilization doing the sending. A species that places a message in a bottle and casts it into the ocean of space, knowing the ocean is vast and the bottle is small, but casting it anyway because the gesture is true. 13 years after Voyager 1 was launched, it turned around. In February 1990, as the spacecraft was leaving the solar system, and its cameras were no longer scientifically useful for planetary study, mission controllers sent a command to Voyager 1 to look back, to photograph the solar system from the outside, to take a portrait of home from a distance of roughly 40 astronomical units. The result was a mosaic of 60 frames, a family portrait of the solar system, showing the sun and several of the planets as tiny points of light against the darkness of space. In one of those frames, almost invisible against scattered sunlight in the camera optics, was Earth, a point of light smaller than a single pixel, a pale blue dot, barely distinguishable from the background. Carl Sagan wrote about that image. He described it as a mote of dust suspended in a sunbeam. He reflected on the wars and kingdoms and certainties and cruelties and hopes of human history, all of them contained within that tiny point. He pointed to the smallness of the dot, not to diminish what happens on it, but to clarify it, to suggest that the smallness of our physical location makes what we do to and for one another matter more, not less. The pale blue dot is not primarily a scientific image. It carries almost no information that astronomers could not have calculated theoretically. Its value is not in the data. Its value is in the perspective, the rare and irreplaceable experience of seeing home from the outside, from a distance that makes it small. We have not taken a comparable image from farther away since. Voyager's cameras were turned off to conserve power not long after. No subsequent mission has traveled far enough in the right direction to repeat the view. The pale blue dot remains the most distant photograph of Earth ever taken. These two things, the golden record and the pale blue dot, sit at opposite ends of Voyager's journey. One was placed aboard at the beginning, before the spacecraft had traveled a mile, carrying humanity's attempt to introduce itself to the universe. The other was produced near the end of the primary mission, when the spacecraft had traveled far enough to see its origin as a point of light. Together they form a kind of frame around the entire story. The scientific discoveries in between, the termination shock, the magnetic highway, the plasma density of interstellar space, the echoes of solar storms beyond the heliopause. Those are the content, but the frame gives the content its weight. These were not instruments alone, traveling through the outer solar system on a data collection mission. They were artifacts of a civilization, carrying its sounds and its greetings and its music, traveling outward into a darkness they could measure, but not illuminate. They still carry those things now. The record is still bolted to the side of each spacecraft. The music is still there. The greetings in 55 languages are still there. The sound of rain and surf and a human heartbeat, encoded in the grooves of a gold-plated copper disc, traveling through interstellar space at 38,000 miles per hour, waiting with no particular urgency. In the patient way that only objects in space can wait, the power is running out, not quickly, not dramatically, slowly, in the way that processes at the edge of the solar system tend to unfold, measured in watts rather than events, in fractions of a percent per year rather than sudden failures. The radioisotope thermoelectric generators aboard each Voyager spacecraft convert the heat released by the radioactive decay of plutonium-238 into electrical current. That decay is continuous and predictable. It cannot be stopped, and it cannot be replenished. With each year that passes, the amount of heat produced is slightly less than the year before. The current generated is slightly less. The power available to the spacecraft's instruments and transmitters is slightly less. When Voyager 1 launched in 1977, its power systems produced roughly 470 watts. By the time it crossed the heliopause in 2012, that figure had declined to around 250 watts. By the mid-2020s, it had fallen further still, not far above the threshold below which keeping all remaining instruments powered simultaneously becomes impossible. The response to declining power has been a long, careful process of prioritization. Instruments that were no longer returning useful science were turned off, one by one, over the decades. Heaters that protect certain components from the cold of deep space were switched off, allowing those components to freeze, accepting that they would no longer function in exchange for preserving the current needed elsewhere. Systems were placed in lower power modes. The engineering teams that manage the spacecraft, a dwindling group of specialists, some of whom have worked on the mission for decades, continue to monitor the available power and make decisions about what to keep running. The goal is to keep at least some science instruments operating for as long as possible. Every additional measurement Voyager can return from interstellar space is a measurement no other instrument currently can make. Even degraded, aging, partially functional instruments on a spacecraft launched in 1977 are, in the regions Voyager now occupies, irreplaceable. The Deep Space Network continues to listen 3 antenna complexes, one in California, one in Spain, one in Australia, positioned around the Earth, so that at least one of them always has a line of sight to the relevant part of the sky. The largest dishes are 70 meters across, their surfaces painstakingly shaped to focus the faintest possible signals toward the receivers at their centers. Even so, the signal from Voyager 1 arrives with almost immeasurably small power. Detecting it requires long integration times, periods during which the antenna collects signal, and the electronics accumulate data, building up enough information to distinguish the transmission from the background noise of the cosmos. The signal travels for more than 22 hours before arriving. A command sent from Earth today will not reach Voyager 1 until tomorrow. The response, if one is sent, will arrive the following day. Communicating with a spacecraft at the edge of the solar system is an exercise in patience and precision, a conversation conducted not in real time, but across a 2-day delay at the speed of light. At some point, the conversation will end. Estimates place the final loss of meaningful communication sometime in the late 2020s or early 2030s, though the exact timing depends on how the power continues to decline and which systems can be kept running with the remaining current. At some point, the transmitter will no longer have enough power to send a signal detectable by even the largest antennas, or the last functioning instrument will fail, or the engineering team will reach a threshold below which maintaining contact is no longer possible. On that day, the signal will simply stop. There will be no explosion, no catastrophic failure, just the quiet end of a transmission that has continued unbroken for nearly 50 years. The antennas will listen for a while longer, as they always do when a signal is lost, checking and rechecking. And then, in time, the listening will stop too, but the spacecraft will continue. There is nothing in the environment Voyager now occupies that will slow it down in any meaningful way on human timescales. The interstellar medium is so thin, so close to a perfect vacuum, that the drag it exerts on the spacecraft is negligible beyond all ordinary reckoning. Voyager 1 is traveling at roughly 17 kilometers per second relative to the Sun. It will continue at that speed, in that direction, for longer than any human time frame can comfortably hold, in roughly 40,000 years. It will make its closest approach to the dim red dwarf star Gliese 445, passing within about 1.5 light years of it, which is close only in the context of interstellar distances. In 100,000 years, it will be farther from the sun than it is possible to usefully imagine. In millions of years, the solar system it left behind will have changed in ways that cannot be predicted. In billions of years, the sun itself will have aged toward the end of its life as a main sequence star. Through all of that, unless it strikes something, and the probability of striking anything in the vast emptiness between stars is extraordinarily small, Voyager will keep drifting, cold, dark, powerless, silent, its instruments no longer measuring, its transmitter no longer broadcasting, its cameras long since turned off, but the golden record will still be bolted to its side. The sounds of Earth will still be encoded in its grooves. The greetings in 55 languages, the music, the rain and the surf and the heartbeat, the images of a pale blue world and the life that covered it, all of it preserved in the cold and the silence. Traveling outward into the galaxy at 38,000 miles per hour, without urgency, without destination, with no particular hope of arrival. Two spacecraft launched in 1977, designed for 5 years, still speaking, still measuring, still sending data across billions of miles from the space between the stars. They rewrote what we knew about the edge of the solar system, the distance to the boundary, the shape of the heliosphere, the moving surface of the heliopause, the magnetic structures within the boundary region, the thin and structured medium of interstellar space, the subtle behavior of the magnetic field at the crossing, and the distant echoes of solar storms reaching beyond the sun's direct domain. 7 corrections to a model that was honestly built and correctly revised when the data returned, and when the science was done, when the last measurement had been made and the last transmission had faded. These 2 small machines would continue outward, not because anyone commanded them to, simply because there is nothing in the void to stop them. The edge of the solar system is not a wall. It is not a line. It is a balance, a dynamic, breathing, magnetically threaded region where the sun's long reach finally gives way to the galaxy around it. Voyager crossed that balance. It measured it from the inside. It sent back what it found, and somewhere beyond the range of every antenna, beyond the reach of every signal. In the darkness between the stars, 2 golden records are still traveling, still carrying the sounds of a world that made them and sent them outward with a question it did not expect to have answered. Sleep well. Somewhere in the dark, the last signals are still crossing the distance, for now.